Hello everyone, and welcome to the session number 8 of this lecture series entitled Excel in Structural Engineering. In the previous session, we completed all the conditional formatting statements of our output cells and tested the Excel template ability to calculate the design strength for a couple of cross-sectional scenarios. Today, we will perform the following. First, we will assign the locked and hidden properties to some of our Excel template cells. The locked property will protect the locked cells from being changed by the user, and the hidden property will prevent the user from seeing the formulas of the hidden cells. Note that locked and hidden properties will not become active until the sheet is protected. We will see how to do that in a minute. Next, we will create a dynamic graph for the strength reduction factor phi as a function of the steel strain at the layer farthest from the neutral axis, which is epsilon t. This is done in order to reflect the ductility status of the beam. The dynamic graph changes whenever the input parameters are changed by the user. Let's start with the first part, where I will lock some of the cells in our Excel template and hide the formulas in some other cells. Let me first reduce the size of the marginal columns here and here, and I'm gonna hide the ribbon from here. I'm gonna select all the cells in my Excel sheet, then right click, Format Cells, and then I'm gonna go to Protection. Sometimes number or alignment is activated, so make sure to go to Protection, and here I'm gonna empty all the boxes and then select a tick for the locked box and then click on OK. This will lock every cell in this Excel sheet. But you need to pay attention to the fact that I need the user to be able to insert values into the input parameters. So I'm going to select the input parameters here, and I'm going to select Format Cells again, and I'm going to remove the locked tick here so that the input parameters will be available for the user to change. Next, I'm going to select all of my output parameter cells, including this one here, and then I'm going to right click, Format Cells, and this time I want these cells not only locked, but I want them hidden as well. And I'm going to click OK. Note that the locked and hidden properties have not been applied yet. You need to protect your sheet for the locked and hidden properties to be activated. So let's do that. I'm going to go here to Review, and I'm going to select Protect Sheet. Here you have to pay attention to a couple of things. Make sure that only Select Unlocked Cells is checked, and remove the tick from everything else. You need to scroll down a bit. Sometimes here you can see a tick next to Edit Objects. If the Edit Objects box is checked, then the user can change the position of the figure, for example, and I want the Excel template to be locked and everything to remain in place. Therefore, make sure that nothing here is ticked except for Select Unlocked Cells. Next, I'm going to insert a password to protect my sheet. You will be asked for this password in case you want to unprotect the sheet, so make sure that this password is strong and make sure to remember that password so that you will be able to use it again. I'm just going to insert, for the sake of demonstration here, a very simple password, 1234. You will be asked to confirm the password, 1234. Click OK. Now, if you try to click any of the cells in the Excel sheet on screen, you will see that these cells are locked. except for these cells here, which are the input parameter cells, where the user should be able to insert different values for the different input parameters in order to study different cross-sectional scenarios. Therefore, these cells are not locked. They are available to the user so that the user can insert the required input parameters. Now, if we try to click on any of the output parameter cells, we can see two things. First of all, these cells are locked, so the user cannot change the content of these cells. Additionally, when we click on any of these cells, the associated formula with that cell is hidden. Usually when you click on any of these cells here, you will be able to see the associated formula here. But now that we have used the hidden properties, the formulas associated with the output parameter cells are all hidden from the user. This Excel sheet is now ready. In the next step, we want to create a dynamic graph that shows the strength reduction factor phi as a function of the steel strain at the layer farthest from the neutral axis, epsilon t, in order to reflect the ductility status of the beam that we are studying. Let's go ahead and start with that. I'm going to create a new sheet in this workbook. This can be done either by right-clicking on the existing sheet here and then clicking on Insert Worksheet, or you can directly click on the plus sign here to have a new sheet created. The number here doesn't really matter. In your case, it will be sheet 2 if you are using a new sheet. I've already created a table that I'm going to copy and paste in order to save time. I'm going to go to sheet number 2 and paste it here. Please pause the video and take your time creating such a table here. I'm going to fix the width of the columns and start inserting the required values. Let's first take a look at this figure here. Let's consider in this figure this point here to be the origin. Consider this to be a coordinate system such that this point here is your origin, your 0, 0. This is your x-axis and this here is your y-axis. So I'm gonna draw a graph with these lines here relative to this origin of this coordinate system. Let's do that. Now, the term dynamic refers to the fact that I'm not going to be inserting constant values. I'm going to be referring to parameters from my Excel sheet here, such that whenever the user changes the input parameters, the output parameters will change and the graph will change accordingly. So I will start now inserting the required parameters. Please bear with me. I know that at this particular point in time, not everything is clear to you, but once you look at the greater picture, you will see that it is doable and it is not really that hard. Here I'm gonna insert a 0. Consider this as your x coordinate and this here as your y coordinate. So the benchmark or the starting point would be 0 and 0.65. Next, I want to use the value of epsilon y, which is the yield strain, so I'm going to hit equal and then type epsilon. You can see that Excel shows you different alternatives, so select here epsilon y and then click enter. This is what is meant by dynamic linking. Now, whatever value is assigned to epsilon y here in this Excel sheet, it will automatically be assigned to this value here. So epsilon y with 0.65, then I'm going to use the upper limit, epsilon upper limit. This value here, I'm going to associate it with 0.9, and then I'm going to add epsilon y to the upper limit and put these two values here. So I'm going to say here this is equal to this value plus this value, and associated here with 0.9. Let me explain what I'm doing. I'm going to show the ribbon and go to insert. Let's have a figure with straight lines. Let's have it here. Let's clear the data. I don't want this, and I don't want this. Let's build the figure from scratch. Let's tell him to select the data, add. In the X, I want these values, and in the Y, I want these values. So you can see that what I actually did is I drew this figure here, but not in terms of constant values. Rather, I used the formulas which are present here in my Excel sheet to calculate these output parameters in order to draw a dynamic figure that will change whenever the parameters inserted by the user are changed. Next, I want to draw a vertical line here and another vertical line here. These vertical lines will represent the boundaries between the different zones in this figure. Remember that we have a tension controlled zone here, a compression controlled zone, and in between we have a transition zone. So I'm going to construct these two vertical lines here and here to represent the boundaries between these zones. In order to do so, I'm going to insert here as the first value epsilon y, which is the yield strain, and a 0 for the y-axis. This will be the point here. Then I will also use epsilon y again, but associated with 0.65. I will do the same thing, but for this line here, which will start here at y0 and will end up here at y.9. And the value associated with the phi value at this particular point is the upper limit for epsilon t. So I'm going to use the upper limit for epsilon t with 0. Again, the upper limit of epsilon t, but this time with 0.9. Let's draw these lines and see what's going on. I'm going to come to the figure here and select data. Let's add on the x-axis these values, on the y these values. There you have it, the first line. Now let's add another one for the second line, x values and y values. We can click on this line here and change its color to red, for example, and the marker as well, and the fill. Border is filled, okay, and the marker. Perfect. Now for the other one as well. In red, and the marker as well. I'm going to mark it in red. So these here represent our boundaries between the zones that we have. Now we want to plot a single point that shows the status of the beam that we are studying, which is here. So we need to insert a value for the x, and we need to insert a value for the y. For the x, the value is nothing but epsilon t. which is epsilon t for the beam that we are studying, and it's a dynamic value because it will change whenever the user changes the input parameters. So I'm going to click here, epsilon t. Next, we want a y value for that. Whatever the value for epsilon t is, the value for phi associated with it will be obtained from here, from this value here. So I'm going to just say here that I'm going to associate this with the value phi. And click enter. I will stop here in order not to make this session too long, and I will see you again in upcoming sessions. Best wishes.